we're going to introduce this idea of acids and bases a little bit more clearly. In the past, we've kind of just categorized them as a broad concept, but now we're going to see exactly how they're defined. The overview for this unit is going to start off by looking at just properties of acids and bases, but also look at how the chemistry of this stuff works. And then eventually we'll talk about acids and bases as a reaction, and then deal with something called titrations. First, a quick overview of properties of acids and bases. I'll let you take a look at this, at these properties. Most of this is fairly familiar. You probably have heard of acids tasting sour. Please do note that we generally don't want to just taste things to see if they're sour and then determine if they're acids. Many of the things that taste sour is because of the acid content, but there are also a lot of other acids that are very corrosive and very harmful too. So please do not just start tasting things to see if they're sour. Acids also change litmus paper to red. You may have seen this before in some old experiments, just taking like a solution of something, dipping a little piece of paper, and then it turns red. Acids will generally react with metals and a lot of times generate H2 gas, hydrogen gas. Acids will also react with bases to form water and a salt in a neutralization reaction. That'll be covered a little bit later. And then finally, acid solutions conduct electric current. We know that because acid solutions, acids we know are electrolytes. Electrolytes are substances that, of course, break apart when they dissolve in water, and therefore they're able to carry electrical current. Couple of nomenclature things. This is old stuff. I'll let you take a look at this between binary and oxyacids. This is worth noting because you have to be able to translate between names and formulas and vice versa when it comes to acids and bases. Speaking of which, let's go and take a look at how bases compare. Aqueous solutions of bases taste bitter. Once again, do not just go around tasting a substance and see if it's going to be bitter, therefore determining if it's a base. A lot of times things that are very bitter tasting is because of the basic content of its materials inside of it. Bases change litmus paper instead of to red, they change them to blue. Dilute solutions of bases feel a little slippery. A lot of times you get the texture of it makes it a little bit slippery. And then bases react with acids to form water and a salt in a neutralization reaction. Once again, will be covered much later. And finally, bases conduct electric current because bases are generally ionic compounds or undergo ionization, which of course allows it to generate ions in solution. Therefore, it's going to conduct electricity. All right, now to really get into it, we're going to break this down into acid-base theory. So a lot of this, again, will seem to be at first a little bit messy, but actually is fairly consistent with something you might already know, / what we've already learned before. All right, so let's try this out. Acids and bases are actually some substances that have to be defined a little bit more broadly. So we're going to use the definitions here to help us get there. First of all, we're going to use this this first theory. It's called Arrhenius theory. Arrhenius, Arrhenius. Arrhenius theory is basically a very simple one. This is a primitive definition of how acids are defined. The definition says this: it's a chemical compound, of course, that increases H plus ion concentration when this substance is dissolved in aqueous solutions. So I can basically just take a step back, grab a sample of some chemical, throw it in some water, and if the resulting solution has more H plus in solution, it's going to be considered an acid. Now, more directly though, the thing is H plus is a very kind of a shortcut / casual way of referring to the substance that actually exists. If you remember, it's actually increasing the hydronium ion. Hydronium ion is H3O plus. So this is really what you're looking for. If H3O plus concentration increases, the substance is an acid. If you kind of just sort of casually say, hey, H plus ion increases, yeah, that it's an acid. But again, more accurately, it'd be H3O hydronium. Now, we also have a distinction between strong and weak acids. Strong acids are substances that completely ionize. So if you can see here, right, H3O, right, this is HNO3, not even H3O, HNO3 right here. This is a substance that is a strong acid. And I'm telling you that it's a strong acid. And you might also remember that from previous content. When that gets dissolved into water, what happens actually is that the water will absorb or take on, not absorb, will accept an H plus ion. Therefore, it'll form H3O plus, right, the hydronium ion. You also will generate NO3 minus because the HNO3, right, the H is removed. That then leaves you with NO3 minus to form this other substance, right? That's a complete ionization. Weak acids, however, on the other hand, weak substances only partially ionize. And so these are substances that don't, again, have a straight arrow. In fact, they have an equilibrium arrow, suggesting that the reaction goes in both directions, right? So the forward reaction goes this way. There's also a reverse one that happens at the same time, and it happens at the same rate because, again, we're talking about equilibrium. Either way, the same process occurs, right? Because if you just take HCN, pure HCN, you dissolve it in water, what does the resulting solution have? The solution ends up having some H+, right? Some H3O hydronium ion. And so because it increases the concentration, this HCN substance, that's going to end up being an acid. You see that again, it does transfer an H over to the H2O. That makes H3O plus and CN minus. But of course, since it is a weak substance, sometimes this reaction right here, or these results, these products here, they can then go the reverse direction and recreate these substances. Now, remember that this is an equilibrium, so that means all four of these substances are present in solution at any given moment. It's just that, again, to go this way and to go that way, it's happening at the same rate. This last one here, CH3COOH, this definitely doesn't follow the normal formula that we expect, right? We always expect H's to be in the front of your acids formulas. That's generally true. But even without that information, knowing that this is going to end up being an acid, how can we tell that this substance right here is an acid, right? Well, we're dissolving it in water, but also notice what's being produced. H3O plus. That means it's going to be more H3O in the solution than was before you dissolved this substance. And so therefore this CH3COH, this right here, is going to end up being considered an acid. Right? It's going to be specifically an Arrhenius acid. Now, this is again somewhat intuitive. I think there's some degree of understanding that if you dissolve some of these substances, you're going to generate some H+. You're going to have some hydronium ion in your solution as a result. But this is just very, very explicitly defining that. On the other hand, you have Arrhenius bases. Arrhenius base is a chemical compound that increases OH minus ion, right? So again, this one is like kind of the counterpart to H+. This is the OH minus ion. So strong bases are going to completely dissociate, right? NaOH right here, you dissolve that in some water, you separate it into Na plus and OH minus ions. This is actually true for any ionic compounds as a whole, but within the broader group of ionic compounds, we're looking at just bases. What's the key here? It increases OH minus, right? So the result of you dissolving NaOH in a solution increases OH minus concentration. Therefore, this is considered an Arrhenius base. Weak bases, on the other hand, right, not ionic compounds. These are actually going to be weak bases. This is an example of NH3. What happens here is that it ionizes, right? So it again forms an ion, but it does so by taking an H from water and then snagging that bad boy, and then it end up making NH4 plus and OH minus. How that happens, again, isn't really necessarily the key. The key here is that it increases OH minus when it comes to this definition of bases. So NH3, this is considered an Arrhenius base. Right? It follows the Arrhenius theory of bases. Like we said, this is a very primitive version of this. One quick comment here is that we're going to talk about protons. The word protons, this is going to be prefaced for the next thing, but the idea here is that they talk a lot about protons when it comes to acid-base behaviors because, well, again, a lot of times it's about moving that H plus around. So as you see here, right, the term proton is used because you see that the normal hydrogen, any normal hydrogen, if it's an acid or if it's by itself or whatever, it's going to be a hydrogen 1. If you remember hydrogen 1, whenever you have this notation, this 1 is like a mass number, right? That's the sum of the protons and neutrons. So if you were to count it out, right, you know you have one proton, right, because that's the atomic number of hydrogen. There's only one electron because it's a neutral atom, and then it's going to have 0 neutrons because that's how it's defined. When hydrogen atoms, however, separate from the rest of the compound, what happens is that the H plus, or the H atom, becomes H plus, right? So when something becomes H plus or something becomes positive, that means it lost some electrons. Well, hydrogen already only had one electron to begin with, so that means it's going to be just one proton hanging out. So literally, an H plus ion is the same thing as one proton. So whenever they talk about protons being moved around, it's basically going to end up being a hydrogen ion. So that gets us into the next definition. This is going to be the Bronsted-Lowry theory. So the little O there, kind of like that Swedish or Norwegian O thing. Anyway, the Bronsted-Lowry theory is a little bit different. If you remember, Arrhenius acids defined the acid-base behavior by having the substance being dissolved in water. This one doesn't necessarily have to be. You can definitely have this be dissolved in water, but it's not always guaranteed. Let's see how this breaks down. The idea here is that a Bronsted-Lowry acid is a substance that acts as a proton donor, right? It talks about giving the proton. Remember, this proton that we're talking about here is still that H+. So we're giving the proton away. A Bronsted-Lowry base, on the other hand, again, this is always talking about kind of like a counterpart here, is basically then going to be a proton acceptor. So it's going to accept the H+. So whatever proton is given up by the acid will be accepted by the base. Let's go and take a look at some examples. So let's go and take HCl. There's a substance that we're going to dissolve in water, right? So the HCl ends up being a gas, but as you put it in water, it will dissolve. And what happens as a result here is that you get H3O plus and Cl minus. Now, what exactly happened here? Well, instead of looking at just the fact that H3O plus is generated, right? That's an Arrhenius definition. We see that, yeah, H3O plus is generated, so we know that HCl, that's an acid. But let's take a look instead, not at H3O plus, but instead let's follow the path of a hydrogen ion. So if you see here, H3O plus is generated, Cl minus comes as a result. That's because this H right here, this hydrogen ion, was transferred to the H2O, the water. That transfer means that HCl, this is acting as a Bronsted-Lowry acid, right? Because again, it gave up the H. On the other hand, water, this acts as a Bronsted-Lowry base, right? That accepts the H plus, that therefore generating H3O plus and Cl minus. So that's how we can define the acid and base here, right? The key to this is looking over here. What exactly happened to go from here to here, right? What did it take? Because we know that this has one additional H, right? Because H2O now has H3O. And because it's positively charged, we know that this H2O, right, this one right here, would have accepted the H from here, therefore making H3O plus. Let's take a look at the second example, right? So this one is going to be hydrochloric acid reacting with ammonia. So once again, what am I looking at here, right? So I have substance A, substance B, these two substances right here hanging out. It's going to end up producing NH4 plus Cl minus, right? So again, how did it get to this? Well, starting with my reactants, it looks like my NH3 right here, right? That became NH4 plus. That means it took on an H, right? It accepted an H plus. And that creates NH4 plus. And as a result, Cl, right, that was left over here, that becomes Cl minus. All right, so what's the key here? Now, the key here, again, is looking at what happens. So let's follow the path, right, of the H. What do the H's do? And since HCl gave up the H here, that becomes Bronsted-Lowry acid. NH3 here, however, on the other hand, accepted it. So that becomes the Bronsted-Lowry base. I'm just going to do Bl base, Bl acid. So what exactly am I trying to point out here? Remember, we're trying to compare this to the Arrhenius acid and Arrhenius base. The Arrhenius acid and Arrhenius base is a very, very primitive definition that requires you to dissolve it in water. But nothing here actually shows anything about water. It's not even assumed, right? Remember, if you see AQ as a state of matter, that means water's around, but this one doesn't even have that. So really what we're saying is that this is, again, something that can actually have a broader application. You can have Bronsted-Lowry acids and bases involving water, as you see here in this case. But there are also examples that don't involve water at all, that don't involve anything involving H3O plus concentration, anything involving OH minus concentration, to also have acid-base behavior. This one, again, just transfers H directly here. So this wouldn't even be an Arrhenius acid or base at all. It's a, however, Bronsted-Lowry acid, Bronsted-Lowry base, because you're transferring a proton. Real quick, this is a monoprotic acid. Let's kind of break that word down. Monoprotic acid means that these are acids that only have one acidic proton, right? The word here meaning that as an acid, it gives it up, right? It can be given up. But monoprotic means just one, right? Mono meaning one, protic referring to the proton or the H plus ion. So in this case, right, HCl, this one, the example we've seen several times now, this is going to be monoprotic because you only have one H that it can give up, therefore monoprotic. What about something like this? Well, this is actually acetic acid, right? This is acetic acid. You see that there's lots of H's in here. In fact, there's a total of 4. So some of you may have wondered, why is that H always by itself? Why can't I just write C2H4O2? That's because this is representing the fact that this is the only acidic H, meaning this is the only H that's given up. These other H's are non-acidic, these 3 in the middle here. And so what you have happen is that H is given up, is given to this H2O. You create H3O plus and C2H3O2 minus. This is a monoprotic acid. Polyprotic acids, on the other hand, as you can imagine, poly means multiple. So that means these are acids that have lots of atoms that can be given up. And that's polyprotic. Only one proton is given at a time, so kind of in a stepwise fashion. Within polyprotic, you can also have very specific diprotic or triprotic. Both of these are polyprotic, because di means 2, tri means 3. But these are acids that have 2 or 3 acidic protons. You can see here in this diagram, this right here, that's my polyprotic phosphoric acid. And basically what this is doing is giving up one H at a time, right, because it's going to act as an acidic proton here. So it gives up the H to the H2O. That generates H3O plus as usual, and H2PO4. But it's not quite done yet, right? So this substance can then just come on right around here, right, to make it the next step. So now it's going to give up another proton, right? H2, there's 2 of them here, it's going to give up one of them to make now HPO4 2 minus, right? And then that then comes around here, HPO42 minus, right, was generated from the second step. This last step right here is going to give up the H and once again generate another substance, but that shows you that this has a 3 total acidic protons. It's a triprotic acid. Finally, we're going to look at acid-base theory number 3, and this is the last one we'll cover. This one we're actually not going to do a ton with. I really just want to provide this as a definition and then as a background. But effectively, this is going to be a concept that actually relies on lone pairs to define acid-base behavior. Remember the other definitions. Arrhenius requires there to be an aqueous solution. Bronsted-Lowry requires there to be a donating of H plus and accepting of H plus. This one's actually, again, even broader. So how they define this one, instead of using H's and whatnot, they actually just look at electrons. So they don't even use atoms. They don't even use actual like substances like that. They use little electrons here to define it. So what this means is that with Lewis acids, this is a substance that accepts a lone pair to form a bond. A Lewis base is a substance that donates a lone pair to form a bond. Now, why do they go to this length to be able to define it? That's a little bit beyond our scope, but do know that chemists have a much broader definition of acids than just H pluses and such. Here's one example, and then we'll finish it here, is that this example of boron trifluoride, right, if you could actually draw it out or write it out, look like that. Or look like this guy right here. And then ammonia gas, which is, you've probably seen this once or twice now. Ammonia gas looks like that. And then also is drawn out right here on this molecule. Those two are actually going to combine to make a new substance. And this is, again, not really something that you and I would necessarily see a whole lot of or be familiar with, but this is actually an acid-base reaction. So what happens here is that the very, very specific, and we zoom in just a little bit right here, is that this very specific pair of electrons right there, that's a lone pair on that central nitrogen right there. And it's actually going to be donated and be given to this boron right here, which accepts it. So this, again, is basically a transfer, or not even transfer, we're just kind of putting it there in that space. And that results in a new bond now that exists between the boron and the nitrogen. Again, the actual details of this we're not really going to get into. I just wanted you to recognize that this is going to be an acid-base reaction, but defined by the Lewis method, or the Lewis definition, where, over here on the right side, this NH3 is going to act as the Lewis base because it has that lone pair that it can donate. And then the BF3, or actually this guy, I should be circling that one actually accepts the lone pair, so that ends up being the Lewis acid. All right, so that's the big breakdown here. Again, you have 3 different acid definitions. Arrhenius, which is the simplest, most primitive one. Bronsted-Lowry, which is a lot broader and can encompass a lot of the Arrhenius behavior, but doesn't require the aqueous solutions. And then this final one, Lewis theory, which actually just almost seems like it's a completely different one, but really just revolves around lone pair donation and acceptance. All right, that'll do it.